All right, in this video, I'm going to show you how you can use support vector machines in order to classify fake banknotes. The data, again, comes from Kaggle, so you have to go on Kaggle and search for banknote UCI. So as soon as you search for banknote UCI, it will take you to the very first data set. Go there and click on data. You would find the data set there that you can download. It's a fairly small data set, but it is a very interesting data set. There you have a bunch of observations about dollar bills, basically, and those are images. However, instead of giving you the images or their matrix format, they are going to give you some metrics after wavelet transformation on the image. And you can read about wavelet transformation because I really don't know exactly how that works. But the point is, based on image data and wavelet transformation, they come up with a few metrics that can summarize that image in terms of variance, skewness, kurtosis, entropy. These are the four features you have, and then the final one is the class, which is either 0 or 1, 0 indicating real bills, whereas 1 indicating that is a fake bill. So the task here is to use support vector machines in order to classify the dollar bills into fake or real using these four images. So go ahead and download this data set and make sure that you put it on a folder that you are going to create your Jupyter Notebook app. So I'm going to do it and download it on my desktop. So I'm going to go ahead and save it there, and then make sure that you extract it on the desktop as well. And once you have done that, you can go ahead and create a Jupyter Notebook in the same folder. So because I have created that data set on my desktop, I have to go ahead and create a Jupyter Notebook on the same folder, which is on my desktop as well. So I'm going to call it banknote classification using SVM. All right. The very first thing that I'm going to do is to go ahead and import the usual libraries: pandas, numpy, matplotlib, and seaborn. So I'm just going to import all of these. Import numpy as np, import matplotlib.pyplot as plt, and we're going to use seaborn as well. So I'm going to import it as SNS, and finally I'm going to put matplotlib inline. I'm going to run it to make sure that everything is right. So once we did that, we have to go ahead and read the CSV file that we just downloaded using pandas. So pd.read_CSV, and the name of the file is banknote authentication.csv. Make sure that you put it inside quotes, and then you assign it to an object. In this case, I'm going to call it banknotes. Banknotes. All right. So just to check that everything is nice, I'm going to take a look at the banknotes, and you can see that you have variance, skewness, kurtosis, entropy, and finally the class. If you want to get a little bit more information, you can type in banknote.describe so that you get a descriptive statistics table about your variables. One of the things that I am interested at is to see the distribution of classes. I want to know what percentage of them are fake and what percentage of them are real. So you can do that with the count plot in Seaborn. So just type in sns.count plot and then identify the name of the data set, which is the banknotes, and then the column in the banknotes that you want to create the count plot, which is the class column. That's why I typed in class here. And it will give you this. If you want to get rid of this part in the output, you just can say plt.show. And then that label up there is going to go away. So one thing to note here is that the data is very nicely distributed. You have almost the same number of fake and real bills, indicating that this is an oversampled data, because the percentage of fake bills is actually very low in a randomly selected data set, and that would not be very helpful if you want to train a machine learning algorithm. And one solution for that is to oversample from the events that are very rare, in this case the bills that are fake, so that the machine learning algorithm can be properly trained. And here you see the result indicates that you have very similar proportions of fake and real dollar bills in your data set. Okay, before we continue doing the machine learning and training our algorithm, one thing that we can do is to take a look at the correlation in the data set and see if we can get any hints from the distribution and correlation of the features with each other. So I'm going to go and use the Banknotes dataset again and just type in core, and it will give me the correlation table. However, I can create a very nice heat map based on this correlation table that is going to be very easier to interpret. So what I am going to do is to put the results of this correlation into an object. So basically create a table based on the results of this correlation table, and I am going to call it correlation matrix. And to make it a little bit easier, I just call it core matrix. All right. So when I do that, the contents of this correlation table are going to be put inside this object correlation matrix. And then I can go ahead and say sns.heatmap, and then give it the name of the dataset based on which I want to have the correlation table. So let me do this step by step so that you'll see exactly how each step is going to change. So this is the heat map that it will give you. It's not really useful. The very first thing that I want to do is to get rid of this thing, whatever that is. So that is with just plt.show, and I do that and that thing goes away, right? So one of the things that I want to do is to annotate this so that I am going to see the correlation values printed in each of these cells, and that is with annotate is equal to true, and you get the correlation values. In this case, the values are printed very nicely. There's no problem with that. But however, sometimes, like in the previous video where I did the heat map for confusion matrix when we were doing digit recognition, these values were written in the scientific format, just to make sure that it will be in a format that we really like. You can go ahead and say format is equal to G. Okay. Sorry, this you have to just in FMT instead of format. So FMT is equal to G, and you will get this values, which is not the best format that you can get. So the best thing to do is actually go back and remove this, because you don't want these many digits. So this is much better. The other thing that I want to do is that I want to get rid of this color ball because this does not make any additional information for me. So I'm just going to type in C bar is equal to false. And when you do that, this thing is going to go over. So it's much nicer. Now, the other thing that I want to do is to change the color map. So I'm going to choose C map is equal to blues. And we get something like this, which is much better. Now, one thing that you would notice is that here, if you want, you can have these negative values to be in a darker shade. So basically, if you want to reverse the order in which these shades are assigned to these colors, using the same color map, you just go ahead and add _R here. And here you will get a more meaningful coloring, because the ones that have a higher correlation, regardless of their negative or positive value, are going to be painted in a darker color. Now, one other thing that I really want to do here is that I want to only print the lower triangle part of this matrix, because it's a symmetric matrix. So first of all, the values on the diagonal do not give me any additional information, because I already know that the correlation of each variable with itself is 1, and then it is symmetric. So here you have skewness with variance, and here you have variance with skewness, and it is the identical number. So I want to remove this upper part of the matrix. I can do that with heat map using the mask option, and what mask does is basically going to mask one part of the plot based on wherever you are asking it to mask. So in order to define where to mask, I have to go one step up ahead and basically go ahead and use the numpy function. So I just say type in np ones like, and then use my correlation matrix. So what does ones like function do? It creates a matrix that is the same format of whatever you're giving it. So basically what we are telling Python to do is to create a matrix that looks like the correlation matrix. So let me run it so that you see that here we have 1, 2, 3, 4, 5 by 5 array here created by NumPy for us that it looks like the correlation matrix, because the correlation matrix is also a 5 by 5 matrix. Now, the other thing that I want to do is that I want to change these values to Boolean values. So instead of 1, I'm going to have true, and that is with dtype. So you say dtype is equal to bool. And we run it again, and you see that instead of ones, now you have true. So this is the first thing. Now, the other thing that I want to do is that I want to only say keep the upper side or the lower side of this matrix. And since this is going to be my mask, basically I will only go ahead and keep the upper triangle, right? And in order to do that, you can use another NumPy function. So let me go ahead and type in np triu, and that stands for triangle up, or upper triangle of whatever this is. And so basically here you have a matrix, and I put that as an input to another function called triu, or the upper part or the upper triangle part of this matrix. And when I run it, you will see that it will only keep the upper part as true, and the lower part is going to be labeled as false, right? So this is going to be my mask. I'm going to assign it to an object, and this is going to actually be my mask. And now I go back to sns.heatmap and use the option mask and say mask is equal to mask. So this first mask is the feature in the heat map function, and then the second one is actually the object that I just created. So it's going to basically create a mask corresponding to the mask that I just defined here, which is going to be true for everything that is on the diagonal or up, meaning that it's going to mask the upper part of the heat map, and only the lower triangle is going to be shown. Okay, let's see what is wrong here. Okay, I forgot to put a comma here. And when I do that, you will see correlation table shown as a heat map, and you only have the lower triangle. So it's a much easier thing to read, and because we actually reversed the color coding, it is showing the correlations between variables that are stronger, as actually, in a higher shade of blue. All right, so now one thing that I want you to notice here is that, of course, there is a high correlation between kurtosis and skewness. There is also a very high correlation between variance and class. So what does it mean? You can create a pair plot to investigate this in more detail. So you can just type in sns.pairplot and then just give the name of your data set as an input. So what this will do is going and basically create plots for every pair of the features and also the outcome in your data set. So it takes a moment, and this is exactly how it's going to look like. Let me make it a little bit smaller. So you're going to have 1, 2, 3, 4, 5 rows and 5 columns, and each of them is going to be basically the distribution between each pair of the observations that you have. So for example here, by the way, variance and variance is going to be the distribution of the variance and so forth. So that is why you see on the diagonal, you see the distribution of each variable. One thing to note that is this distribution is very similar because this is the exactly this thing that we already looked at. And now one thing to look at is that, for example, we noticed that the variance of class and variance, the correlation between variance and class is negative, and it's very high. And when you look at here, you can see the same phenomenon. It looks like that the observations that have very high variance are all in the class 0, and the ones that have very low variance, meaning that the extreme left corner here, are all in the 1 variance. Now, if you add the color here by the option of hue, and you say that I want to use different colors for different values of class, then you can get an even nicer plot. Let me make it larger. So when you add the class as a coloring option, then you lose the pair plots with the class. So it's going to become a 4x4 plot rather than a 5x5. However, it's going to use the colors in order to show the pairwise plots. And one thing that is very interesting here is that when you look at the distribution of variance, you would see that at the class 0, you have observations that have very high variance, right? And then for class 1, you would have observations that have a very low variance. And at the very extreme, at the very low variance, they are all observations in class 1 in the orange color, and at the extreme right, at the very high variance, you have only observations that are in the class blue or class 0. So this is why the correlation between variance and class was very high. In contrast, if you look at the variable entropy and its distribution between the two classes, they are almost indistinguishable, meaning that there's no correlation between entropy or class, right? At the very end, you have observations from both the blue and the orange class, 0 and 1, so at the left end of the distributions, you have observations from both classes. All right, so that is enough of data exploration. Just let's go ahead and create our X and Y data sets. So I just go ahead and type X is my banknotes dot drop, and I identify the column that I want to drop, which is my class. Again, we now know that this is going to only keep the features and drop the label data set. Just to make sure that we have done everything correctly, we can take a look at the head, and you can see here I only have the features. I'm going to also go ahead and create my Y data set, which is going to be the banknotes. However, it will only include the class column. All right, and everything runs perfectly. All right, now one other step is to go and import train test split from Sklearn model selection. I'm going to learn from Sklearn dot model selection, import train test split, and I'm going to create my X train, X test, Y train, and Y test data sets using the train test split, and make sure that you correctly import the basically X and Y data sets. And test sizes, I'm going to choose 0.2. 20% of the observations are going to be kept for testing. Training is on 80%. And like always, I'm going to define the random state to be 1984 and run it to make sure that there's no problems. All right, and now we can go and import the support vector machines from Sklearn. Okay, from Sklearn, import SVM. Make sure that you're using it in lowercase. And then you can say svm.svc is the support vector classifier that we're going to use. And I'm going to call this the classifier. Make sure that you are opening and closing the parentheses. So from now on, whenever I call classifier, it's actually going to go and support use the SVC function within the SVM. And now I can actually go ahead and fit a model using the classifier that just defined based on the X train and Y train. And after it's run, you can actually go ahead and score it. So classifier.score using X test and Y test. And you see that I get 0.9963, a very, very high score for classification. It just shows that how good the support vector classifiers are at these conditions here. Now, I want to go ahead and make some confusion matrix. So what I will do is that I will create a Y pred, and that is basically the predictions. and that is going to be based on my model. So I just say classifier dot predict, and the input to that is going to be my test features. And once I have that, before I can create my confusion matrix, I actually have to go and import the metrics from Sklearn. And then we can just I can just type in metrics dot confusion underscore matrix, and I have to give it the correct values, which are in y-test, and the predicted values, which are in y-pred. And this is your confusion matrix. Now, just like the previous videos that we use the heat map, I'm going to put these values in a table. So I'm going to call it confusion matrix. Confusion matrix. All right. And now I'm going to create a heat map based on it, and just say SNS that heat map based on the values in this object, which is the confusion matrix. And I'm just going to do it again step by step. First of all, I want to get rid of this code here, or whatever it is. So I'm just going to type in plt.show. It gets rid of this. And then I want the values to be annotated. So I'm going to go ahead and say annet is equal to true. And when you have it, these values are there. And this is what I was talking about. You see that these are written in scientific format for some reason unbeknownst to me. And then you can go ahead and say fmt is equal to g. And now that fixes it for you. The other thing is that I'm going to use the same color map, blues, as I used before. It's a much nicer way. And finally, I'm going to get rid of this C bar using the C bar is equal to false option. And then I have a much better presentation. Now, I can also go ahead and make this confusion matrix a little bit better. Well, the very first thing is that I'm going to give it a name and also put the access labels there. So I can go ahead and say plt.title confusion matrix for SVC. And then I can go ahead and say plt x label. And for my X label, I'm going to call it predicted values. And for my Y label, I am going to call it actual values. And then you have the actual values and predicted values. The other thing that I'm going to do is that instead of these, 0 and 1s, I'm going to give them labels, right? So instead of 0, I want it to be real, and instead of 1, I want it to be fake. So in order to do that, you have to use the ticks. So type in plt.say xticks, and the very first thing that I do is to use the np.arange. 2, and when I do that, it basically is going to create two numbers, 0 and 1, corresponding to here, 0 and 1. And because I want them to be pushed in between, I'm going to add 0.5 to them. So 0 plus 0.5 is going to be here, 0.5, and then 1 plus 0.5 is going to be 1.5. It's going to be here, right? So I'm going to just type in plus 0.5, that is going to be the location of the ticks, and then the actual labels that I am going to give the ticks are real and fake. So here you see that it is, instead of 0, I have real, instead of 1, I have fake, and I can do the exact same thing for the while text as well. And I'm going to have real and fake. So when you look at this confusion matrix, you see that there is only one instance where the actual value is real, but the predicted class is fake. And in every other case, it has correctly made the classification, and that is why the accuracy is so high.